Okay, in this video we'll be talking about coordination compounds. So last video we saw what are transition elements, what are their properties, and how electronic configuration essentially controls their properties and their interaction with different elements in periodic table. So in this case we'll talk about different types of compounds that these transition metals can form. And one of those compounds is called the coordination compounds or coordinate compounds. So up until now, you guys have learned about two different kinds of compounds, one of them being the ionic compounds, which is formed between a metal and a non-metal. And then there are molecular compounds, which is formed between two non-metals. So for instance, ionic compound is like sodium chloride, NaCl. Na is a metal, Cl is a non-metal. So that makes it ionic. Here they essentially transfer electrons from one atom to another, which makes them ionic. And the bond that is keeping these two atoms together is an ionic bond. The other kind of compound is molecular compound, which is composed of two nonmetals. For instance, if we talk about water, H2O, hydrogen is a nonmetal, oxygen is a nonmetal, so that essentially makes that compound a molecular compound. Now, the kind of bond that keeps the atoms in a molecular compound together are called covalent bond. So in that case, both the atoms that are bonded together to each other by a covalent bond are sharing one electron each. So they are sharing electrons together to fill up their octets. Coordination compounds are the compounds where one of the atoms kind of donates to a lone pair to the other atom, and that kind of bond is called a coordinate bond, where the electrons, essentially like a lone pair, is completely donated. So today we'll talk about coordination compounds. What you see right here, this is an example of a coordination compound. So every coordination compound, how can you identify it? You would see that there is a certain part of this compound, a certain formula of this compound would be written in square parentheses. Okay, so whatever is written in square parentheses, that is called the complex part of that compound. So for instance, what we have here, if this is a compound, it consists of this part in parentheses and a certain part which is outside the parentheses. So then we have CONH3 whole 6 in parentheses and Cl3 outside the parentheses. So whatever is inside the parentheses, for instance between this, is called the complex ion. Whatever is outside the parentheses is called the counter ion. So what essentially this means, in this case of a compound, this complex ion is acting as a cation, right? So it consists of cobalt and ammonia, and this is a whole ion in itself. So up until now, you guys are familiar with some polyatomic ions, right? I'm just going to put an example right here. This has nothing to do with coordination compounds, okay? I'm just trying to explain you uh, like for instance right here, if this sulfate ion is a polyatomic ion, which means that it consists of multiple atoms. Similarly, what you see right here, CONH3 whole 6 is a coordination complex or complex ion. This is also a polyatomic ion, right? And this is just a complex ion. It's called a complex ion. Why? Because it consists of a coordinate bond which is formed between cobalt and ammonia, and this will make more sense as we talk about this. But essentially it consists of this ion which is called the complex ion. So whatever is included in square parentheses is a complex ion. Always remember that. It can be cationic, it can be anionic. In this particular example it is cation. So whenever we write a formula, remember in chemistry, it's always cation followed by anion. It's always cation written first. For instance, HCl, H plus Cl minus. Cation is the positively charged ion. That is the one that is always written first. NaCl. You can pick whatever example you want. It's always cation followed by anion. So in this case also, we have the cation written first. In this case, cation is a complex ion. How do you know that? Because it's in square parentheses. So always just remember whatever is in square parentheses is part of the complex ion, and whatever is outside that is the counter ion. Now again, counter ion can be positively charged or negatively charged depending on what compound we are talking about. Now this is about where we're talking about the complex ion, right, in a coordination compound. Now let's further break this complex ion down. So what we have here, we have chloride ion. You should know how you name Cl minus. That is a chloride ion. This is a counter ion, and this is a complex ion. Now let's break apart our complex ion. It consists of cobalt, parentheses, ammonia 6, and if I break this apart, it is going to be 3 plus, and I'll explain you why I have 3 plus here. But anyways, let's just see what I'm want to express from here. For now, essentially it consists of a metal which is going to be always a transition metal. So in this case that is cobalt, and then whatever is outside or whatever is apart from that transition metal is called a ligand. So there is always a transition metal, and there are going to be certain amount of ligands. Now that can be same ligand, multiple different kinds of ligands. In this case, the only ligand that we have is ammonia. Okay, so what does a coordination compound consist of? It consists of a complex ion, which is always going to be in square parentheses, and a counter ion. Now it's not necessary if it has a counter ion, or if it's a compound, it will definitely have an ion. But if it's a coordination ion, it would just give you ion like this. And the next thing is that in a complex ion, it will always consist of transition metal, and everything else apart from the transition metal is called a ligand. Now, what do these ligands do? These ligands essentially are donor of electrons. So remember, our metal is always positively charged. Metals are always cationic in nature. They are always looking for electrons. So in order to make this compound, these ligands, they donate a lone pair of electrons. So they always have an extra lone pair, and that lone pair is donated to the metal ion, and that forms a coordination bond. That's why these complexes are called coordinate complexes. Coordination complexes or coordination compound, right? So let's take a look at the definition of a ligand. So the ligand of a complex ion are the molecules or anions with one or more donor atoms. Each donor atom donates a lone pair of electrons to the metal ion to form a coordinate covalent bond. So the bond between coordination compounds, remember, is called the coordinate covalent bond. Both electrons in the shared pair come from same atom. And what are these ligands? These ligands can have multiple different kinds. So you will have to kind of memorize that. There are some ligands that are called monodentate. Monodentate means mono means one, dent means teeth. So when you write a coordination compound, you usually assume that if this is the metal in the middle, this is my transition metal, it has formed coordination bonds with multiple ligands, and each of these ligands essentially forms a bond with the metal, just like it's um, acting like a teeth for this particular metal. So that's why it's called dentate. Mono means just one ligand. Monodentate ligands are the ones where one ligand, for instance, if I have this metal M and this ligand L, one ligand will be forming a bond with metal, only one bond. So each ligand can only form one bond. That is a monodentate ligand. What is a bidentate ligand? A bidentate ligand is going to be something which has two donor atoms. For instance, if I have this ligand which is, let's say, En. Okay, En can have two different coordination bonds. So the same molecule can form two bonds with metal. So that's why it is called a bidentate ligand. So it has two teeth with the help of which it can interact with the metal. And then there are polydentate ligand, which means that this particular ligand will have more than two donor atoms, so it can form multiple bonds with the metal. So one single ligand can form multiple bonds with the metal. So that is a polydentate ligand. Now let's look at some common ligands in the coordination compounds, and you need to be able to differentiate between these compounds. You should at least know their names. I don't expect you to know their formula for, not for at least these ones in the bottom, but you should definitely know their names, and you should be able to recognize them when you see their formula written out. But I don't expect you to know their formulas by heart. So the monodentate ligand examples would be water. So if you see water has oxygen, oxygen has two different lone pairs, and it can donate one of these lone pairs, so it can only form one monodentate bond, one bond with the metal in coordination compound. That's why it's called monodentate. Then there's fluoride ion. Fluoride ion also has multiple lone pairs, but it can only make one bond. So F minus, you should know their symbol for at least the top ones. These are the easy ones. These are polyatomic ions that you should have already known their names and their formulas by now. Then there is cyanide ion. Cyanide ion also has um, the extra electron lone pair that it can donate. Now there are the next example is hydroxide ion. Hydroxide would be OH minus, cyanide would be Cn minus. Then there is ammonia, which is NH3, chloride, which is Cl minus, thiocyanate, which is SCN. So essentially instead of Cn, it is SCN minus. Here, thiocyanate can form a bond with either the S, so it has two atoms that can donate electron. Either S will donate the electron or N. Now either way, it can only form one bond with the metal because it's a monodentate ligand. Next example you see here is nitrite, which is ONO minus. So here also again nitrogen has a lone pair that it can donate and oxygen has a lone pair that it can donate. But idea is that only one of them will be donating electron at one time point. Now let's look at certain examples of bidentate ligand. First is ethylene diamine, which is also abbreviated as EN. So you should know its name, ethylene diamine. Ethylene means eth means two. Ethylene or ethylene means two carbons. So what you see right here, two carbons, and each of these carbon is interacting with one amine. So that's why it's called diamine, because this molecule has two amine molecules. Amine is NH2. So this is the structure of ethylene diamine. What you should know, sometimes when you're writing the structure, it can be abbreviated as EN. So instead of writing the formula, you can just write En and make two different bonds. And why can it make two bonds? Because there are two nitrogen or two amines that each of them has a lone pair which can interact with metal to form a coordinate bond. So this ethylene diamine, one atom will be forming two bonds with a metal in the middle. Similarly, there's another example of bidentate ligand, which is oxalate. Oxalate is essentially C2O4 2 minus. So you can see the formula can be written out as simple as that, C2O4 2 minus. That means it's an oxalate ion, and each oxalate ion will be forming two bonds with the metal, two coordination bonds with the metal. Two of these oxygens essentially can donate one lone pair each. Now, certain examples of polydentate ligand means, so you can see right here, when there's only one nitrogen in ammonia, it can form one bond. When there are two amines, two nitrogens, it can form two bonds. Now, if I have multiple amines, for instance, in here, diethylene triamine. So there are diethylene, so two ethylene groups, CH2, CH2, two of those, and triamine means three amine groups. So therefore, each of them can form a bond. So it is going to form three bonds with the metal. Then you see triphosphate, which again can also form three bonds. Each of these oxygen can form one bond with uh, the metal ion. This is triphosphate. Next, you see ethylene diamine tetraacetate ion, which is also abbreviated as EDTA. This is a very popular compound which is used as a chelator. We'll talk about that in a little bit, but what does it do? Each EDTA molecule is 4 minus, and it can form multiple bonds. So you can see right here 1, 2, 3, 4, 5, and 6. So the highlighted ones Highlighted atoms are the ones that can each donate a lone pair to a metal. So it can form 1, 2, 3, 4, 5, 6, 6 bond. One EDTA molecule can form 6 bond with the metal. So it can donate 6 lone pairs to the metal at one point. Therefore, it is called polydentate. So you should know their names by now. There's water, ammonia, fluoride, chloride, cyanide, thiocyanate, hydroxide, nitride. And examples of di or bidentate is EN, ethylene diamine, and oxalate, which is C2O4 2 minus. And lastly is polydentate. For instance, diethylene triamine, it can form 3 bonds. Triphosphate, it can form 3 bonds. And EDTA, ethylene diamine tetraacetate ion, which can form multiple bonds even as of each EDTA. Okay. Now I said to you there is a term called chelation. EDTA is a very good chelator that is used in chemistry. What do I mean by chelation? Chelation essentially means that when you have a certain compound or certain ion like this, it has so many teeth that it can interact with the metal and kind of engulf that metal inside of it. That is called a chelator, something that can essentially just interact with the metal and kind of engulf it. So remember I said that each of these metal will form one bond with the ligand, right? And there are some ligands that can form multiple bonds, some ligands that can form two bonds, one bond, or multiple bonds. So if a ligand can form bidentate or polydentate, meaning if it can form either two bonds or more than two bonds, then those ligands usually can form ring around the complex ion. So for instance, if I'm making a complex between cobalt and En was a bidentate ligand, ethylene diamine. So for instance, right here you see CO. Again, each of these, remember, can form two bonds. So I have one En and you see here three En. So one, two, one more En, and then one and two, one more En. So I'm not writing the complete formula, I'm just writing En, which also means that I understand this. It's ethylene diamine. So this ethylene diamine, you can see how this ethylene diamine has all its teeth. Each of the ethylene diamine has its two teeth on cobalt. So it's kind of has engulfed this cobalt. It's not going to interact with anything else. That's called chelation, the process. And these ligands are called chelators. Okay. A complex ion containing this type of structure is called chelate because the ligand seems to grab the metal ion like claws. So it has kind of like stuck the metal within its structure. Next example is you see here right here EDTA, right? Each EDTA has 6 donor atoms and form very stable complexes with metal. So you can just imagine that one EDTA molecule can form all these 6 bonds, just one EDTA molecule. So it's a very good chelator. It can interact with the metal and just keep it attached to itself and does not let it go or interact with anything else. Now, I already explained to you that the components of a coordination compound, for instance, right here in this example, the square parentheses are written first and the ion is written at the end, which means chloride ion is the anion in this case, Cl minus, and then this CONH3 whole 6 to the power 3 plus is our counter ion or the complex ion in this case. So, and how many ligands are there in this case? There are 6 ligands. So there is 6 ammonia, which means there are 6 ligands that are interacting with cobalt. And if I look at the other example, which is K2PtCl4, so if you look at this example, how can I dissociate this? Whatever is in the parentheses, remember that is our complex ion. So in this case, it's going to be platinum times Cl4. And then since I'm breaking it apart, it has to have a charge, right? So we'll figure out what the charge is later on. But right now I have potassium ion, which is K plus. And then we have this ion, which would be, what would be the charge here? 2 minus. How do I know that? Remember when you make the when you go from the ions to their structure, to their chemical formula, that's how you do it. If how do you get NaCl as NaCl? Because you have Na plus Cl minus, so you cross these charges over to get to NaCl, right? How do you get MgCl2? Mg is Mg2 plus, Cl is Cl minus 1. So you cross over these charges without the sign, everything's positive, and that gives you the chemical formula. It's exactly like this here. This is the cation now, this is the anion. So the whole charge of the compound is 0. It's a neutral compound, right? There's no charge. Charges are usually written as a superscript on the right side. There's no charge, which means potassium is the ion. And remember, potassium belongs to first A group. It always has a +1 charge. So there are two of those. So 2 times +1 plus the total charge of the compound. It consists of this platinum chloride, which we are interested in figuring out what is the formula for it. So I'm just going to assume it's X. There's only one of those, is equal to total charge of 0, which means X is going to be, to do this, I'll have to subtract 2 from on both the side. That would give me X as -2. That's how I know what is the charge on platinum, PtCl4, right? So those are coordination compounds. Now there's another term which is called the coordination number. What is it? The coordination number is defined as the number of bonds that are formed by central metal ion directly with the ligand. Now there can be different ligands that are involved, or there can be just one ligand that is involved in a coordination bond. But the idea is, what is the total number of bonds between the center and the ligand, between the metal and the ligand? That is a coordination number. That's all. So for instance, if I pick this example, what is the coordination number of cobalt in this? So cobalt is right here. Now remember, whatever is inside the parentheses is a complex ion. So now we have to figure out, if I were to think of the structure, I have cobalt in here, then there is one Cl, and this is bonded directly to cobalt. How do I know that? Because it's all in parentheses. As long as it's all inside the square parentheses, it's all directly interacting with the metal ion. So first thing you should identify, this is my metal, and I have two different types of ligand. One is chlorine and the other one is En, which is ethylene diamine. So there are two chlorine, so I drew two chlorine, and let me draw it here, right? So I draw two different chlorines. Now what the next thing is, I need to draw two En. Again, remember, En is a bidentate ligand, which means if I have one molecule of En, it will form two bonds with cobalt. So I can have one more En, it's going to form two bonds with cobalt. So each of these En would be forming two bonds. So now what is the coordination number? Coordination number, remember, is the total number of bonds that are formed by the central atom, irrespective of what ligand it is. So total bond is 1 bond, 2 bond, 3 bond, 4, 5, 6. So total number of bonds is 6. So coordination number is 6. Very simple, as long as you just understand the terminology and how to use it. So now we'll talk about, actually let's just talk about the coordination number and shape of some of these complex ions. So again, like you have studied before, all the compounds, be it molecular, ionic, they always have a shape or a geometry that they follow, and that geometry is dependent on how many bonds are present, how many atoms are interacting with each other, how many atoms are charged, how much charge, total charge is present. So for instance, right here, if a complex ion only consists of one metal and two ions, two ligands, sorry, I shouldn't say ion, two ligands interacting with it, it's going to be linear. If something has coordination number is 4, there are two possibilities that are possible. One is square planar, other one is tetrahedral. So I don't expect you to kind of memorize this all, the whole thing here, but one of them is square planar, the other one is tetrahedral, and the last one is the coordination number of 8. If it's 8, it's essentially would have a geometry of octahedral structure, and here are some of the examples. Okay, so you should just know, if it's 2 coordination number, it's always going to be linear. If it's 6 coordination number, it's always going to be octahedral. If it's 4, it can be between square planar or a tetrahedral structure. Square planar is usually, now let's not get into it right now. If we want to discuss it, we'll discuss it later in the slide. So what do we know for a coordination compound as of now? We know that it can consist of 3 different scenarios. One is where it consists of a complex cation. So whatever is in the parentheses is going to be written first with simple anionic counterparts, and whatever is the counterpart will be written outside. The next example is a complex anion with simple cationic counterparts. So for instance, the counter ion is going to be written first, followed by the parentheses, which consist of our um, coordination ion, complex anion. So it consists of these 2 scenarios. There is also a third scenario where we have a complex cation and a complex anion. For instance, this complex cation is also complex, anion is also complex. So that is also another scenario that is possible. I will not be dealing with that third scenario in your course. We'll only stick to the ones which has complex ion as a cation, or the complex ion is acting as an anion. Those are the major 2 scenarios. Okay. Now we come to 2 different things. There are actually 3 things that are very important in this chapter that you should understand. One is how you can figure out what is the charge or the oxidation state or oxidation number of the metal ion. The second is that we should be able to write the formula of a metal transition compound if I know the name. And the last thing is I should be able to name a coordination compound if I know the formula. So those are the 3 things that we'll try to focus on. So the first is, how can I determine the charge of the metal ion that is present in a coordination compound? Now remember, the metal ion will always carry a positive charge. If you for some reason are getting a negative charge of just the metal ion, that means there is some error. You should go back and check your work. Okay, so let's see how we can figure that out. For instance, this is a compound, cobalt ammonia 4 Cl2. I'm not talking about the actual name here because we haven't learned that yet. So in this case, what you're going to do, how would you find the charge of the metal? It's exactly the same idea that we do for any ionic compound. So what is the total charge of the compound here? 0. How do I know that? There is no charge written on the right superscript. Charges are always written on the superscript on the right side of the formula. So if there's nothing, that means 0. And whatever is the charge of the complex is equal to charge of the metal ion and the total charge of the ligand. In this case, it has broken. Let's first break the total compound. So we are going to break this into ion. The first ion would be CO NH3 whole 4 Cl2 parentheses minus NCl, sorry, plus NCl minus. How do I know that? Because Cl is going to be dissociated. Cl always carries a negative 1 charge. So if that is negative 1, there's only one ion and there's only one complex ion that has to neutralize the charge of this chloride, which means it will be plus 1. Now once I have this ion, I can assign each of these entities or each of these atoms that is present inside the complex ion with a charge or the total oxidation number, and that is going to be equal to the total charge of the ion, which is plus 1. So this consists of 2 things. One is the positive ion, one is the negative ion. So now we are only interested in cobalt, so I will only pick the cation here. So what is the total charge of cobalt is something that we want to figure out. So I can write cobalt right here. I have one of those. Then there are 4 ammonia, and you know ammonia is a neutral compound, so each ammonia is going to be 0, plus 2 chloride ions here, so 2, and each of that carries a negative 1 charge, and all of this added up is going to be equal to 0. Oh, not in this case, is going to be equal to the charge of the ion, which was plus 1. So now from here we can solve for cobalt. So this plus 1 again is coming from the charge of the ion that you see right here. So you're going to split your cation and the anion separately and then figure out what is the charge of the complex ion or the metal in the complex ion. So for instance, in this case, this is going to be cobalt. Plus 0 minus 2 is going to be plus 1. So what is cobalt going to be? We will add 2 on both the sides. That would give us cobalt as plus 3. So in this case, the charge of cobalt is plus 3. And what is the oxidation state of cobalt? Plus 3. What is the coordination number in this case? It is forming one bond. Each ammonia, remember, is a monodentate ligand, so each is going to only form one bond with this, so that is total of 4 bonds. And then there are 2 chlorine, and each chlorine can also only form one bond, so that is 2 more bonds, which means again the coordination number is in this compound is also 6. Now you'll see for most of the coordination compound the coordination number is 6. Sometimes there's also 2 and 4, but most of the times it's 6. So let's try some question. Give the coordination number and charge of the central metal ion in the following coordination compound. So let's begin with the first one. In this case, the question is asking what is the coordination number. Coordination number means how many bonds. That's all. And what is the charge of the central metal. So in this case, what is my complex ion? I'm going to start with Na2 parentheses ZnOH 4 parentheses close. So to find both of these, first thing we have to dissociate this. So there are 2 sodium ions, so it's going to be 1 sodium plus for each one of those, right? And there are 2 of those, which means to neutralize, make this compound neutral, this complex ion, which is ZnOH whole 4, should have a total charge of 2 minus. Now the question is, what is coordination number? Coordination number is again how many total bonds this metal is forming. The metal is forming 4 bonds with 4 ligands. So each of these would make it coordination number of 4. Next is, what is the charge of the central metal? How do we find the charge? Again, to find the charge, I'll put everything equal to the total charge of the ion. So Zn, I only have one of those. 4 times hydroxide, each hydroxide is minus 1. And this total is going to be equal to minus 2. Why minus 2? Because the total charge of the ion is 2. So now we are just solving for Zn. So Zn negative 4, because it's 4 times negative 1 will give it negative 4 is equal to negative 2. So Zn is going to be, I add 4 on both the side, it will be negative 2 plus 4, which means total charge of plus 2. So in this case, zinc is carrying a charge of plus 2, and coordination number for zinc here is 4. Now let's do the second example. So you guys can try this example on your own before I show you the answer. So you can pause the video, try the question, and then come back and look for the answer. Okay, so the second compound is potassium with cobalt, water, and remember C2O4 is an oxalate ligand, oxalate ion, so you should remember that. So if I start with my compound, it is potassium, in parentheses it's cobalt, water holds twice, C2O4 hold twice, parentheses. So the compound is neutral, and what is the complex ion? Whatever is in the parentheses is the complex ion. Whatever is outside is the counter ion. So if I break this, it's going to be potassium ion, which is a counter ion, and I only have one of those, and potassium always carries a positive one charge, which means the second ion that I will have will carry an, to neutralize this positive charge, it has to carry a total charge of negative 1. So I can break this ion as negative 1. So now I can figure out what is the coordination number. What is coordination number? Remember, each water is a monodentate ligand. So each water is going to form one bond, and that makes it 2 times 1. And this is coordination number, so number of bonds with the metal. And then we have oxalate. Now remember, oxalate is a bidentate ligand, so one oxalate will form 2 bonds and I have 2 of those, which means 2 times 2 will give me a total of 4. So that's 2 plus 4. Again, the coordination number is the common coordination number, which is 6. Now the question is, the second question was, after coordination, remember what is the charge of the central metal? So we want to figure out what is the charge of cobalt here. So how would we do that? Again, we use this ion right here. We total up, sum up all the charges and make it equal to the total charge of the ion. So cobalt is something we want to figure out. Plus water. What is the total charge of water? Water is a neutral compound. I have 2 of those, which means 2 times 0. Plus oxalate, and I have 2 of those, and each oxalate, if you remember, the formula for oxalate ion was, I'll write it here, C2O4 2 minus. So each of them carries a -2 charge, and I have 2 of those, so 2 times -2 is going to be equal to what? Oh, sorry, it's equal to a total charge of -1 right here. So now if I solve for this, that means cobalt minus 4 equals -1. So now I rearrange this. So cobalt will be equal to -1 plus 4, which gives it a total charge of plus 3. So that would be the total charge of cobalt in this particular compound. Now let's try the last question, which is Ru, H2O2, ammonia, chlorine, and Br. So this is just, I'm just going over all the components that are present in here for now. Let me clear my screen. In the meantime, you guys can try this question out. Pause the video if you have to, and then you can come back and check, confirm if you have the correct answer. Okay, so let me begin with this part. So the example we have is parentheses Ru, H2O2, ammonia, 2 of those, and Cl2. And outside parentheses I have Br. So whatever is inside the parentheses, remember, that is what is important for me to find the coordination number. So now if I'm just solving for coordination number, let's just first dissociate it. Br minus, and then I have parentheses Ru, water, whole twice, ammonia, whole twice, Cl2. This is all that's in parentheses, and this, if this is -1, this has to be a charge of +1 to neutralize that final compound. So now what is the coordination number of Ru here? Again, we are looking for number of bonds. So there are 2 water molecules, and each water is a monodentate ligand, so it will form 1 bond. Then there is ammonia. Ammonia is also a monodentate ligand, so each ammonia will form 1 bond, so it's 2 times 1. And then there's chlorine, and there's 2 of those, and each chlorine also is a monodentate, which is going to form 1 bond. So fluorine, chlorine, bromine, you saw the example of fluorine in the slide, which means chlorine, bromine, iodine, all of those are halogens as well. So the total number of bonds that has formed is 2, 2, 4, 5, 6. Again, the coordination number would be 6. Now the next part is the charge of the central metal. So again, we'll start with the charge of Ruth. So Ru, we'll say Ru. The next molecule that we have is water, and we have 2 of those, and each water is 0. Why? Because water is a neutral ligand. Then I have ammonia, 2 of those, and each ammonia is also neutral. It has no charge, so 0. Plus chlorine. Each chlorine, again, there are 2 of those, but each chlorine is -1. It's a halogen. They always have -1 charge. And this totals to a total charge of +1, which is written right here. So now we are just solving for Ru. Ru -2 equals +1. Now if I rearrange that, it would give me Ru equals, I add +2 on both the sides, that would give me Ru as +3. So that would be my total charge of the central metal ion. Alright. So that is how you solve questions like this. These are fairly simple questions. You just have to know have to understand the idea behind it, and this should be fairly simple to complete. Okay, now let's look at The next type of question that you can see here. So, like I said, we have to figure out what is the formula of a coordination compound. How would you find out what's the formula of a coordination compound? Just follow these steps, like written right here. Okay. When writing the formula for a coordination compound, remember the cation is written first, then the anion. It's always cation followed by anion. Then the charge of the cation is or are balanced by the charge of the anion to make the compound neutral. So that's always what we do. For instance, if we make NaCl, we put one Na, one Cl. Why? Because we are trying to neutralize the charge. So Na has a +1 charge, Cl minus has a -1 charge. We want to neutralize it. That's why you need one of each. And exactly what you will do here. You do that crisscross approach. Then the next rule is charge on the complex is the sum of the charge on the metal and charges on the ligand. So how do you find what is the charge on the complex? Complex ion, what we have just been doing. So whatever is in the parentheses, add the charges of everything and that would give you charge, which is right here for the full ion. When more than one kind of ligand is present, this is important. When more than one type of ligand is present, you always write the neutral ligand first. So for instance, if I have water and C2O4 2 minus in the same compound, water will be written first in the formula. So neutral before anionic ligands, and anionic ligands, they both are written in alphabetical order. So for instance, if I have two different types of neutral molecules, so I know neutral comes first, but which neutral will come first? If I have water, which is aqua, and then I have ammonia, which is NH3, they both are neutral, right? So which one do I put first? You're going to use the alphabetical order in that case. So always put neutral followed by charged or anionic, and then both of those are written in alphabetical order. So if you have two neutrals, they'll be in alphabetical order. If you have two charged, they'll be in alphabetical order. And that's it. Those are the rules. But there's also we'll come to those rules later on. Let's just try a couple examples. For instance, if I'm writing a compound between cobalt, so the question is telling me there is a compound between cobalt 2 plus, there is 6 water molecules and 2 chloride, okay, 2 Cl minus, and the question would tell you which one is a ligand and which one is a counter ion. Now you should know what is the ligand and what is a counter ion. So for instance, in this case, the question is telling us 6 water molecules are bound to cobalt ion. So these are ligand. Water is a ligand. The 2 chloride ions are there only to balance the charge. Charge meaning they are counter ions. So they are counter ions, in this case anion. So we are just going to follow our rules regarding writing the formula. So what is the formula? We write down the cation first. So the two things that we have here is, one is the ligand, there's cobalt 2 plus, sorry, that's calcium, it's cobalt 2 plus, and that is interacting with water, right? So when you write the formula, remember the metal has no charge, so I'll write cobalt and then I'll write water, and we have 6 of those, so 6. This would be in parentheses. That would be my one ion. The second ion is Cl minus, and I have 2 of those, so that's going to be Cl2 in minus charge, right? Each of them carries a negative one charge, so that is going to be one of the ions. Now remember, the cation is always written first. This is X and this is minus, and I have 2 chloride ions. So now we first have to identify what is X here. So how do we find that? Cobalt is going to be, let's say we want to figure out what's the charge of cobalt. Cobalt charge is +2, we already know that, right? We want to figure out what is X. So cobalt is already +2. What is the charge of water? We have 6 of those, each water is 0, which totals up to X, which means X is going to be equal to +2 or 2 plus. Which means when I write this formula, I can replace this X. Oh, my bad. I can replace this X with 2 plus. And then I have 2 Cl minus ion neutralizing it, which means these two here and these two chlorides are going to cancel each other out. So if I write the formula, if you write this crisscrossing it, so total charge of Cl is going to be 2 Cl 2 minus, right? So if you crisscross this, that would give you a formula of CO H2O 6 times two of these and two of these. Now remember, you cannot have, when you write the ionic formula, you always put the least ratio that is possible, right? So if I divide both by 2, that would give me one of this, and you usually don't write 1 in the formula, which means the formula is going to be just this right here, because they will neutralize each other when it comes to the number. So that is how you can identify what is the formula of a compound. Next, let's try one more example here. So what is the formula of complex made by Ag plus and 2 cyanide ion? So in this case, the question is telling us we have, wow, what is this? Okay, so what do we have? We have Ag plus and 2 cyanide ions. Decide if the complex could be isolated as chloride salt or potassium salt. Write the formula of the appropriate salt. So the question is saying there is Ag and there is Cn minus. Now you tell me, should I put the counter ion as chloride or potassium? How can we tell that? We'll first write the complex formula for the complex ion. There is complex ion, so in parentheses, there's Ag, which is 1, and then there's Cn minus, right? So let's just put this as here, Ag plus and Cn minus. So it's telling us there is one Ag and there's two Cn minus. So that is my complex, but now I don't know what is the charge when I put these together. So I have to now identify what is the charge of my complex ion, right? So let's identify that. So what is Ag? Ag, there's only one, which means this is plus 1. Oh, each of them is plus 1. The question tells us it's Ag plus. What is cyanide? Cyanide is Cn minus, and I have two of those, so 2 times minus 1. So what is the total charge equal to? That is X. Total charge is equal to whatever the charge of the ion is, right? So that gives me plus 1, negative 2 is X, which is equal to negative 1, which means my formula for complex ion is AgCN whole twice negative 1. So if this is negative, which means what do I have in my formula? This is going to act as anion. So if I want the formula to neutralize it, I need something positive, which is I need a cation, right? And out of chloride and potassium, which one is cation? Chloride is Cl minus, potassium is K plus. I need something positive to neutralize that. So my formula would be K is plus 1 and this is AgCN whole twice minus 1. They are going to cross over and both of them are 1, so they'll cancel each other out. They'll neutralize each other. So Cn, so AgCN, oh, whole twice, and 1 will neutralize each other. So that would be our formula for our final compound between AgCN and a counter ion. So now you should understand this is the complex ion in parentheses. This is the counter ion just there to neutralize our final compound, because it's a compound. Remember, compounds are neutral in charge. Ions are the ones that carry a charge. Okay. Moving on, we have next question. So in this case, what is the formula for the complex made by copper 2 plus and 4 ammonia molecules? Let's try this question out by ourselves. Decide if the complex could be isolated as a bromide salt or sodium salt. Write the formula for appropriate salt. So this is based on the exact same idea. What do we have? We have copper 2 plus. So first write the complex ion, which consists of copper, right? Remember this charges that you see, they don't go in the formula. It's just copper and 4 ammonia. So you just put copper, 1 ammonia is NH3, and you have 4 of those, so times 4, and that's it. That is our compound, complex ion. It has a charge. Now it has a positive, negative, I don't know. I have to identify. So I'm just putting an X right here. Now we'll identify what is X. How do we know that? Copper is plus 2. We know that. Question tells us this is plus 2. I have ammonia, 4 of those, and I know ammonia has a charge of 0. This totals up to X, which means this is totaling up to plus 2. So what is the ion that I have? I have copper, 4 of ammonia, and total charge of 2 plus. What is the counter ion for this? If this is my cation, remember cation is written first. I need anion, so something negative. What is negative? Bromine or sodium. Bromine is the one, bromide is the one that is negative. So Br minus 1. Now to cancel each other and neutralize each other out, we need 2 bromide. So the formula would be CuNH3 4 times Br2. Now the whole charge of the compound is neutral. And that's all. Let's try a couple more example questions. The type of questions you can see from this chapter. What is the oxidation state of iron in the following complex? So what is the oxidation state? Oxidation state essentially means whatever is the charge. So whatever is the charge on iron, that would be the oxidation state. How can I find the charge? Again, we'll begin with what we have seen for now. You don't have to break apart this each time. You can just do the whole compound and make it equal to 0 because the whole compound is equal to 0, right? What do I mean by that? There are 3 potassium. What is the charge of each potassium ion? Remember, potassium is group 1. It's always plus 1. So I have 3 of those. That's why I have 3 outside. Plus iron, which is we want to find out, plus this cyanide. So I have 6 of those. Each cyanide is Cn minus 1. How do I know that? I memorize it. Okay. Add all of this up and make it equal to the total charge of the compound, which is 0. We don't see a charge, which means it is 0. So now I'm just rearranging this to solve for Fe. So if I rearrange this, that would be Fe plus 3 minus 6 is equal to 0. So Fe minus 3 equals 0, which means Fe equals plus 3. So that would be my oxidation state or oxidation number or charge of iron in this complex. Next question is, what is the oxidation state of nickel in following complex? Same idea, nickel is what is we want to find out. So nickel plus cyanide, I have 4 of those. Each cyanide is -1. Total everything up equals to the charge which is outside, which is -2. So in this case, I know nickel -4 equals -2. To rearrange this, I have to add 4 on both the sides. That would give me -2 plus 4, which is +2. So nickel would carry a charge of +2. Next question is, what is the formula for the complex made by Cr, 2 plus and 6 ammonia molecules? Add chlorine or potassium. So Cr, easy. If I'm writing the formula, I put parentheses. There is one Cr, 6 ammonia. Each ammonia is NH3 and each of them is neutrals. That's 6 of those times, oh sorry, parentheses to the power x. Now I have to figure out what is x. Cr is +2. I have 1 of those, so +2. Plus ammonia, I have 6 of those. Each ammonia is 0. Total adds up to x, which is equal to +2. So in this case, my compound is Cr ion times 6 is 2 plus. And I need a counter ion to balance it out. So which one do I need? Something negative. Something negative here is chlorine or chloride. So Cl minus 1. Again, to balance the charges, I need to cross over. So that would give me Cr NH3 whole 6 Cl2. So this is my formula, which is option number C. So that would be my final answer. There you go. It shows you all the answers and how we got them. Now let's move on and try a couple more questions. What is the formula for the complex between Cr and 5 water molecules and 1 chloride ion as ligand? So it's telling you there is 5 water and 1 chloride, and all of them is ligand. Add chloride or potassium ion to form appropriate salt. So we have chloride, which chromium, sorry, Cr is the metal ion. Then I have water molecules, 5 of those. So water times 5. And then there is 1 chloride. So don't forget that there is 1 chloride as a ligand, meaning this is acting as ligand. So if it is ligand, it's going to be in parentheses. And then now I have to figure out what is the charge of this, which is X. So Cr is plus 3. The question is telling me I have 5 water. Each water is 0. So 5 times 0 plus 1 chlorine. So 1 times each chlorine is negative 1 equal to X. So this totals out to 3 minus 1, which would give me plus 2. So my X is plus 2, which means this is a cation. The complex ion is a cation. And I need something negative to balance it out, which would be negative 1. So now crossing these over would give me, I'm just going to erase it right here and put my final number. It would give me Cl2. I need 2 chloride to balance out the total charge of plus 2 over this complex. Now the last part is which the following can act as a chelating ligand. Remember, chelating or chelating ligand is the one which can form multiple bonds, either 2 or more, right? 2 or more bonds. Which one of those? Ammonia can only do 1 bond, water can only do 1 bond, cyanide can do 1 bond. There is one amine. One N can only form 1 bond. There are 2 amines here, 1 and 1. This can form 2 bonds, which means this can act as a chelate. That's it. Next, we'll move on to the next idea, which is how do you name a coordination compound? So there are again rules about naming a coordination compound. What we saw up until now was how do you write the formula for a compound. Now we'll see how do we name a chemical compound, a coordination compound specifically. So again, when you name a compound, you always write name of cation first, followed by anion. How do you remember this? You know NaCl. That's the easiest example. This is not a coordination compound, we know that, but it follows the same rule. Na is Na plus, Cl is Cl minus. We always call it sodium chloride, and we not chlorine chloride sodium, right? We call it sodium chloride because cation is written first. So always cation name goes first, then anion. Within the complex ion, ligands are named in alphabetical order before the metal. So you first put cation. So the first rule is always put cation name followed by anion name. Now you name each of them separately, okay? How do I name the one of them is going to be complex ion. How do you name the complex ion? The ligands are named in alphabetical order before the metal. So metal comes last. Ligands are named first. If it's an anionic ligand, meaning something negative, drop the IDE and add O. So for instance, if it is Cl minus, what is the name of Cl minus? It's chloride. But when it's a coordination compound, you put it as chloro, not chloride. Okay, so you remove the IDE, replace it with O. O. Ligands whose name end in ITE become ITO. Ligand whose name end in ATE become ATO. So everything has to end with an O. ITE, ITO. ATE, ATO. Okay, like nitrite will become nitrito. Carbonate will become carbonato. Okay, oxalate is ATE, will become oxalate. That is about naming the ligand. Now, what is the next thing? A numerical prefix is used to indicate the number of ligands of a particular type. So prefixes do not affect the alphabetical order of ligand. So remember, we put these ligands in alphabetical order, and the prefix is put before the ligand name. So if I have one of those, it's going to be, if it's one, you don't put any prefix. If it's two, you put bis. If it's three, you put tris. If it's four, you put tetrakis. Okay, you only have to learn till here if it's bis, tris, or tetrakis. So 2, 3, 4. And now Again, the bis doesn't affect the alphabetical order. Tris doesn't affect. So it doesn't mean if you put a tris in front of a ligand, it's going to begin with T. That's not the, whatever is the name of the ligand, that would be the alphabetical order. Lastly, a Roman numeral is used to indicate the oxidation state of the metal that can have more than one state. The name of the metal is written and then it's followed by an oxidation state. So if it's iron, let's say, you put a +3, +2, whatever is the charge. And if the complex ion, this is when the complex ion is a cation. If the complex ion is an anion, we drop the ending of the metal name and add an ATE. So usually metal name is written as is, but if it is an anion, you drop the metal name, remove the ending and put an ATE. Now let's take a look at a few examples. So here are some of the names of the ligand that we saw. Now remember, ligand, you think it would be the same name that we call them, but that's not correct. So for instance, please remember this. This is something you have to memorize. Naming, you have to memorize how to name them. And all these names, I do expect you to have them memorized. So for instance, if it's water, it's not called water. It's called aqua. If it's NH3, it's not called amine, it's called amine. A-M-M-I-N-E. Usually amine is A-M-I-N-E. Don't make that mistake. This is amine, but in coordination compound, it's written as amine. A-M-M-I-N-E. That's how I call it, amine, just to remember it. Then there is CO, which is carbonyl. Then there is NO, which is nitro-CO. These are the different kind of names, that not so common names that you would see. Rest everything is very similar and follows the rule that we just saw. So you kind of would have to memorize these four: carbonyl, nitrosyl, amine, and aqua. Don't use water. Okay. Next, the ligands that are anionic, we saw what the name is. If it's fluoride, F minus is fluoride, it changes to IDE, changes to O. So it becomes fluoro. Chloride becomes chloro. Bromide becomes bromo. Iodide becomes iodo. Hydroxide becomes hydroxo. Cyanide becomes cyano. So IDE is replaced with O. Here are name of some more ligands. For instance, you have carbonate. ATE becomes ATO. So carbonate becomes carbonato. This is not something new. These are the ligands that you should know the naming of these ligands by now already. This is from General Chemistry 1. So you should know their naming by now. Then there is thiosulfate, which is S2O3 2 minus. It's called thiosulfato. There is thiocyanate, which is SCN minus. So it's thiocyanato when the bonded through sulfur. It is isothiocyanato when it is bonded through nitrogen. I don't expect you to remember each of these, but definitely remember carbonate, oxalate, nitrate, and nitrite. These you should know because you have already known these names. And then at least CN minus, which is cyanide, right? So oxalate becomes oxalato. Then this is nitrite, NO2 minus. NO2 minus, if it is bonded through oxygen, it becomes nitrito. If it is bonded through nitrogen, it becomes nitro. So nitrite, ITE becomes ITO. So nitrite becomes nitro. It's not ITO exactly, but it becomes nitro. And it becomes nitrito if it is bonded through oxygen. Now what happens to the name of the metals? Remember, name of some metal ion in complex anion. If it is cation, if the complex ion is cation, the name stays as it is. Iron is iron, copper is copper, lead is lead, silver is silver, gold is gold. But if they are in anions, if the complex ion is an anion, so for instance, if this is the cation and my anion is the complex ion, okay, then your name of the metal will change. So iron will become ferrate. Copper will become cuprate. Again, they add an ATE. Remember, we drop the ending of the metal name and add ATE. So just do that. Iron is ferrate, right? Ferrous. So it becomes ferrate. Copper becomes cuprate. Lead becomes plumate. Silver becomes argenate. Gold becomes orate. Tin becomes tennate. Aluminum becomes illuminate. Manganese becomes manganate. Nickel, nickelate. Zinc, zincate. Platinum, platinate. Vanadium, vanadate. Cobalt, cobaltate. So most of those are very similar. The weird ones or something different is essentially here lead is plumate, silver is arsenate, gold is aurate, tin is stannate. Rest everything is same. And also copper is cuprate, not copperate. It's cuprate. Iron is not ironate, it's ferrate. Okay, so these are the ones that you kind of will have to spend some time on, but otherwise rest is you just add an ATE at the end. Oops, I showed you before. Try to name some of these. So for instance, this is an anion. Okay, first thing you have to identify if the complex ion is cation or anion. Complex ion is anion. So what is the rule? I put the ligand name first. Ligand is cyano, it's cyanide, right? So it becomes cyano. Cyano, and how many do I have? I have two of those, so that becomes dicyano. And silver. Silver is if it is cation. Here this is anionic in nature, which means it will be argentate. This is where the name of the metal changes. Now remember it said always follow the metal name with the oxidation number. So I have to find oxidation number of silver here. How do I do that? Again, I'll assume silver is silver. Each cyanide carries a total charge of -1, which totals up to a total charge of -1 because of this -1. So silver -2 equal -1, which means silver equal +1. So this is going to be 1, and since this is an ion, it ends with ion. If it was a compound, you don't put anything. For instance, if I'm naming Na plus, right? Remember, always go back to this example of sodium chloride. If I'm naming Na plus, I don't call it sodium. Sodium is Na. What is Na plus? Na plus is sodium ion. Similarly, you call this ion because this is an ion. It has a charge to it. Okay, so just don't leave it at that. Let's look at the next one. Okay, the answers are showing here, but try to not see the answers and try to name them yourself. So what do we have here? This is again an anion, which means the name of the metal is going to change. First thing. Next thing is you always name the ligand first. So what is the ligand? In alphabetical order. I only have one. I have hydroxide. Remember IDE becomes O. So hydroxide becomes hydroxo. So how many of those do I have? Prefix would be tetrahydroxo. And see, there's no space anywhere. It's all connected. So don't put any spaces anywhere. Hydroxo. And now the name of the metal, which is zinc. But since it's in an ion, it will become zincate, followed by the charge ion. Now let's find the charge. It's going to be zinc. Let's assume that is zinc. 4 hydroxide, so each hydroxide is +1. So zinc plus zinc plus 4 hydroxide is each is -1. Total -2. So that means zinc -4 equal -2. So zinc will be +2. So in this case, zinc will be zincate 2. So don't forget any of these steps because this is all credit or no credit. So it's going to be ligand name followed by prefix ligand name followed by the metal name. The next example is right here. So what do I have here? I have cobalt, ammonia, 6 ammonia ligands. So this is a ligand and this is cationic in nature, which means the metal name is going to stay as it is. What is ammonia called? First, let's write the name of the anion, which is amine. How many of this do I have? 6, which means it's hexa. Now, if I put hexa photo, it's going to make it double A. So you just put one A in between. Okay? Take off one of those A's. You don't put double A's. So hexaamine cobalt, because this is a normal cation. So it's going to stay as it is. And now I put metal followed by charge ion. So let's find what is the charge of this metal. Cobalt is cobalt, plus 6 of ammonia, 8 ammonia is 0. The total charge is equal to plus 3, which means cobalt is plus 3. So I'll put a 3 right here in Roman numerals. Don't put 1, 2, 3. It has to be always Roman numerals. Lastly, I have this. This is going to be a little tricky one. So remember En. En is ethylene diamine. You have to know its name, ethylene diamine. I don't expect you to know the symbol or the structure, but just have an idea. If you have two amines and two carbons, that is ethylene diamine. And again, this is a whole compound. So now it's not an ion. This is a complete compound. So what do? You first name your cation, then your anion. What is the name of the cation? That is an ion. So I'll have to name it separately. What is the name of the anion? Chloride. That never changes, right? NaCl, sodium chloride. So this is the name of the anion, chloride. This is outside the complex ion, so we don't make it chloro, it stays as chloride. Whatever is inside, that naming changes. So let's name this. We'll first put name of the ligand, which is ethylene diamine. How many? 3, which means it's tris ethylene diamine, followed by name of the metal, which again in this case is cationic in nature, so it's going to be same, manganese, followed by charge, and then followed by the final ion, which is chloride. So now I have to find this parentheses. How do I find that? Again, Mn. You don't have to separate it out. You can just start with this Mn. 3 ethylene diamine. And if you remember, each ethylene diamine is neutral. So the total charge is 0. Plus 2 chloride, which is 2 minus 1. And total charge is equal to 0 because the total charge here is 0. So Mn minus 2 equals 0, meaning Mn equals plus 2. So the total charge here is going to be plus 2. That is the name of this compound. Now, next question is, what is the correct name of NiBrCN ammonia 3? Okay. How would we identify what is the correct name? Now you have multiple ligands in here. It's a neutral compound. There are multiple ligands here. So now we have to name them by alphabetical order. So let's name it. Nickel will stay as nickel. This will come at the end. It's a metal, right? So I have bromo. I have cyano. And then I have amine. Amine. Which is alphabetically correct? Amine comes first. Then bromo. Then cyano. How many amine? 2. So it's going to be bisamine, right? So let's see if we can find a name. There's no bis, but there's a diamine. Okay, so we can work with that. Diamine bromocyanonickel 2. Now we have to figure out if it's actually nickel 2. How can we do that? Nickel, let's assume it's nickel. Br is 1 and there's -1 always in Br, so 1 times -1. Cyanide is also 1, so I have 1 times -1. And ammonia is neutral, so it's 0 equal 0. Why? Because total charge is 0. So nickel -1 minus 1 equal 0. So nickel minus 2 equals 0. So nickel is plus 2. So that is correct. I'm thinking the correct answer is B, which is diamine bromocyanonickel. Okay. Now let's predict the formula for these. We have done formula before. Again, formula is also from cation to anion. But now we have to do from the naming formula. So how can we name it? It's very simple. Formula through name through formula is very easy. What do you see? Tetracyano. So let's pick each of these. So tetracyano means I have Cn whole 4. Then it's cuprate. So I have copper and it's cuprate, right? Which it's not copper. Cuprate means the total ion charge is going to be negative because it's an anion. And it is copper plus 1, right? So what would be the formula? It's copper followed by 4Cn, and that's it. Now I have to find the charge of this ion. So Cn, copper is +1, plus each of cyanide is -1. So total charge is equal to X, which comes out to be a total charge of -3. So my actual formula is going to be replace X with 3 minus. Alright, so now let's move on to the next one, which is triamine. So put each of them separately, okay? ANH3, I have 3 of those. Thiocyano. Thio was SCN, and there's only one of those because there's nothing, no prefix before it. And then there's platinum, and platinum is +3. So we have to make a compound between these three. So how would we make that? You write the platinum first. Oh, sorry, pulled out the answer. Don't look at the answer yet. So we'll write the in parentheses, it's going to be platinum first, followed by the iron, which was amine and SCN. Now, remember, we always put the uh, neutral ligand first. So this is partially not correct. You should put the neutral ligand first. So what is going to come first is ammonia, which is the amine, followed by SCN, which is the negatively charged one. And now we put the total charge X. And what is X? We'll find that because platinum is +3 given to us in question. 3 amine, which is 3 times 0. 1 thiocyanide, which is -1, is total equal to X. So 3 minus 1 means +2 is X. So X is +2. So this X, I can replace it with +2. So don't leave it as X, okay? Make sure you give me the final answer. So this is your final answer. Lastly, we have potassium. So potassium is going to be +1. Remember, this is no longer has an ion next to it, which means this is a compound. So I see cation name is always written first. So potassium is my cation. So K plus. Hexacyanoferrate. Hexacyano means I have Cn, 6 of those. Ferrate means Fe, and why is it called ferrate? Because the total complex ion is going to have a negative charge. I don't know how much, so I'm just going to leave it as -X for now. We don't have to find. We'll have to find it eventually. Ferrate is +3. So let's figure out what is the charge of this X ion. If we want the final formula, we need this, right? So 6 times cyanide, each cyanide is -1, plus iron. Iron, it's telling us, is 3 equal to X. So forget about this minus sign for now. I know it's minus. Why? Because if it was a plus or a cation, it would be ion. Because it's ferrate, I know it's an ion. So this is going to be equal to X, which means -6 plus 3 is equal to X. So X is equal to -3. So now how do I write the final formula? It's potassium. First put the metal FeCN6 -3. So now we cross over the charges to balance it out. To balance this charge of -3, I need 3 potassium. FeCN, sorry, Cn6. So that would be a final answer for this. So you just make sure you cross over the charges to balance it out completely. And that's all. So there are a few more examples which you guys can try on your own. What is the systemic name of this? What is the systemic name of this? What is the formula of this? What is the formula of this? So essentially, the kind of questions you'll get from here is either naming the formula, writing the formula from the name, or naming the compound if the formula is given to you. So make sure you understand and remember the naming rules and remember the rules for writing the formula. And those are the major questions that will come from this part of the chapter. There's this last chapter part which I'll cover in the last video, which talks about different forms of isomers of coordination compounds. Along with isomers, we'll talk about a little bit about uh, uh, distribution of electrons, crystal field theory. I am not going to give you much questions from there, but yes, isomers, you should definitely understand what are isomers. So we'll talk about isomers in the next video.